Okay, good morning, afternoon, or evening, depending on the time zone you're in. Thank you for choosing to attend this year's IMSSRS and also opting to listen into my asynchronous talk today. My name is Emmanuel Paalam. I'm an undergraduate computer science major at the University of West Florida, and today I'll be presenting a research project I conducted with the Computational Statistics and Data Analytics Lab at my university, which was focused on learning how to, or not learning, but rather understanding how to utilize machine learning to forecast student dropout. So I did this project under the mentorship of Dr. Ashraf Cohen. Thank you, Dr. Cohen, for being a great mentor. And also did receive a bit of financial support from the Office of Undergraduate Research as well. So also thank you to them. So before actually getting into the methodology of the project itself, in order to provide a foundation for it, I was first tasked with developing a literature review just to better understand what student dropout actually is as an issue that concerns academia, as well as looking into what currently has been conducted to understand or counter it. So while it has decreased relatively recently in prevalence, dropout remains an issue across secondary and post-secondary levels of education and internationally. And it is an issue for administrators, just as they probably want to, minimize waste of educational resources and maximize retention rates for their programs. With that in mind, there is a deep existing body of literature on trying to figure out what the origins of dropout are. Primarily, they're all data-centric, or which basically means what factors contribute to the issue the most. There have been some methodologies developed to counteract the issue as well. So, for example, I encountered the SRSSIE, which is basically a way of using internalizing and externalizing behaviors to assess a student's risk of dropout, things like that. A lot of the methodologies are like self-reporting things, but in recent years, there has also been an increased interest in using AI to assist in the minimization of dropout. So Nicoletti's article is very interesting to propose a lot of theoretical stuff for what an AI program that could assess a student's risk of dropout would look like. Something I want to point back to quickly, the idea that student dropout is a very data-centric issue. I put it that way because a lot of the studies that I was encountering while writing my literature review support the idea that it's multifaceted, basically meaning that there are a bunch of different factors for students, academic and non-academic alike, that can play into the decision to stay in an educational program or not. So it's multifaceted for that reason. There can be academic reasons. There can be things like psychosocial reasons, or other reasons relating to the environment of that the student's in. A variety of different kinds of things that can help to determine or contribute to the decision to drop out or not. So, hearing that, at least I think of a high resolution data set that has a lot of different variables being recorded in it. And I'm sure we all understand a little bit that machine learning, computers, at least computers, I don't know if everyone's worked with machine learning here, but computers are definitely a lot more efficient in terms of time when trying to reason based off of a data set. We break down a huge data set, very dense. It can do that a lot quicker than humans can, for sure. So, given that the issue's high res, as well as general recommendations from the literature as well to develop more effective predictive rather than responsive methodologies, was what encouraged us to look into machine learning as an option for predicting student dropout. The second point there, more effective predictive rather than responsive, I just put in because a lot of the methodologies like the SRSSIE are a bit better at detecting when dropout is more certain rather than detecting it early on, which was more our concern, just for the sake of developing a methodology that is better at guaranteeing reversal can still happen. So we were concerned with detecting it early on and using machine learning to do that, given what I've said. So our research question was, what machine learning model is best suited for dropout prediction? So as I'll explain in the next slides, we were looking into a bunch of different models for solving this issue. One thing I will say is that rather than a full-on product, like something sellable to companies or whatever, the outcome was more so intended to provide findings, meaning that we were trying to secure what best type of model, for example, would be useful for this research question. But we hope that this research project will act as a consulting resource for any subsequent product development. So of course, before you actually get started with machine learning modeling, you need to establish a data set for your models to be based on in terms of the decision making. So we opted to use the Nationally Representative Educational Longitudinal Study of 2002. This is coming from a survey conducted by the National Center for Education Statistics, a decade-long survey that followed American students from their sophomore years of high school throughout their post-secondary years. Ideally, throughout the decade, they stayed in school, or maybe they entered industry at some point. There are 3 follow-ups that occur from the baseline, as you can see in the visual below. That's coming from the website the study information is on. And maybe participants might have dropped out before one of these follow-ups as well. But it follows all participants throughout recording a variety of academic and non-academic factors on them. For the purposes of the study, in which we wanted to attempt to model dropout, predict it early on, we decided to focus on information only on students while they're in high school. So from the baseline when they're in sophomore year all the way to the end of high school, which is the first follow-up. The second and third are going to have occurred post-secondary. The one exceptional variable in this case was F3 overdue. That's a variable coming from the final follow-up F3, as you can see in the visual again below. That variable indicates whether a student participating in the study has dropped out any time during the study. So this was a binary variable that we used as the target, with the rest of the variables remaining after dataset cleaning to be used as predictors. So referring to dataset cleaning, describing that a little more, besides removing all the variables from F2 and F3, there were some students who were transferred into the study between baseline year and first follow-up year. Information on them was removed. A bunch of ID weight flag type variables were removed. Things that weren't necessarily actual information about like the student, environment, nothing. Things that act as weights more so than actual information were removed from the data set. And there was a good amount of columns that did have a significant amount of missing values. As you can see with these heat maps, the leftmost one is meant to display the number of missing values per row. Rows represented by the vertical axis, in each column, which is represented by the horizontal axis. So a lot of the columns per row have a lot of missing values, which are represented by yellow. We decided to remove columns that have more than 10% missing values. So before and after, left to right, the second heat map, the one on the right, shows what our final data set looks like after all of those removals. So as I said, F3 overdue was the target variable for our study. I should mention this now. It's a binary variable, of course. So zeros represent students who had not dropped out at all during the study, and ones represent those who had. So that's kind of explicit labeling allowed us to supervise machine learning models, which require annotation or labeling between classes to train properly. Statistical models we also looked into because, of course, this is us looking at a data set and making predictions based off of it. That's a very stats heavy issue. I wouldn't be presenting here if I wasn't, I guess. But models that fell under those categories we chose and tested comparatively to find the most optimal one. So we looked into logistic regression, which, unlike linear regression, is more appropriate for categorical rather than continuous outcomes. I won't get into support vector machines just because that was not the most well-suited kind of model for us. You can read it here on the slide if you like, but decision trees, random forest, and XGBoost are all based on the same kind of concept of a tree graph. So I guess you can think of a tree graph as a kind of structure that goes between variables from one variable to the next, depending on the value for, in this case, a student at one variable. It'll take you to another variable, and so the structure will continue to work on classifying you based on your value per variable until it can make a decision, in this case, as to whether you're a dropout or not, kind of flowing between one variable to the next, going downward in that way. That's kind of the concept of a tree graph. And all three of these kinds of models are based off of it in some way. Random forest specifically constructs a mean decision tree based off of however many you choose to have it generate. And then XGBoost, rather than creating a mean or average quote unquote tree, will make trees sequentially. So it'll make an initial tree and then boost performance by improving from that tree up to a certain point. So going back to data clean very quickly, beyond column removal, we had to explore some ways to handle other issues that we were encountering after removing a number of columns with a significant number of values missing or ones that weren't relevant for our issue. So there were a number of columns left that had under 10% values missing. So for those, we did decide to keep them, but try to impute the missing values per row using either simple imputation, which is just imputation based on like the mean of a column, for example, or some constant, which did turn out to be a little problematic considering there are different kinds of variables in the data set, some nominal, some ordinal. It was a little hard to manage between those. Multivariate imputation, I might have partly spoiled it already, but multivariate imputation, that's known as MICE, the MICE algorithm in the citation I'm offering here. And it did work a little better. Unlike simple imputation, it iteratively imputes. So what that will do is, instead of doing imputation based on some fixed value, a multivariate imputation will be a little bit smarter and look at rows in the data set where the value for a certain variable isn't missing and do guesstimates based on what's there. SMOTE, meanwhile, was more so for class imbalance between dropouts and non-dropouts. What we found, as I visualize on the left, is that there are more non-dropouts than dropouts in our data set, which of course would be a good thing for educational institutions because you don't want the majority of your students to be dropping out. But for the sake of our study, was something we needed to balance out a little bit. So SMOTE we decided to apply to, unlike traditional oversampling methods, which is what some people might use, we decided to utilize SMOTE as it looks at the current existing number of an underrepresented class, like an oversampling method, but instead of just duplicating those existing instances of the class, which is what traditionally is done, it looks at each one and does a kind of k nearest neighbors thing with the number of students in the minority class in this case. basically creating intermediaries between them until there's a number of them that balances out the number of non-dropouts. So applying all of those methods and everything, we finally got to training and testing our models. And we specifically chose three metrics to test, not test, but assess the classification performance of each. So unlike accuracy, or I should say, accuracy was often very high for all the models. And as you can see, that's probably due to the fact that it's a lot easier for models to classify non-dropouts than dropouts. So overall, classification performance will be very good between dropouts and non-dropouts, or including both dropouts and non-dropouts. Classification will be very easy for the models to perform. But we're interested in how accurately models predict a certain class in this data set, which is the dropouts. So rather than looking at accuracy, we decided to look at precision, recall, and F1 score, which in this case focus on when F3 over due equals 1. That's focusing on the dropout class. So precision, you can think of it practically as throughout all of the students predicted as dropouts by each model, which one was accurately identified as a dropout, or which ones were accurately identified as dropouts. Recall is more so looking into the number of students who were predicted as dropouts and which ones were accurately identified. So precision looks at the entire dropout population and sees which ones were predicted as such. Recall is more so looking at which ones were predicted as such and seeing how many are actually in that class. And then F1 score, you can think of as a harmonic mean between the two. So these metrics were used rather than just like accuracy or something to assess classification performance for these models. So with all that in mind, the best performing model was XGBoost, as you can see here. We were particularly prioritizing F1 score, as it is the mean between precision and recall. So that model, along with mice and smote as add-on pre-processing techniques, did turn out to be the best performing for us. So, of course, XGBoost simple imputation deductively has a higher precision, but given what I said earlier about simple imputation and also seeing that its F1 score and recall are lower than XGBoost mice with smote, we found that the precision, recall, and F1 score rates for mice with smote XGBoost were most favorable, with a specific emphasis on F1 score. So besides that, other findings are that a lot of what we found for optimal model types was in line with the literature. The citation I have here does also suggest using decision tree type models. And also, to our knowledge, there is no other predictive or machine learning focused study that has been conducted on the dataset we used. Some limitations for this study would be that we had a limited set of processing methods, and that could be expanded on more in future work. We also could explore the explainability methods for model behavior. So how student features contribute to predicted dropout likelihood, and rather than looking at the rates for F1 score and whatever other metrics, also assessing what individual variables contribute to those higher metrics. And then, of course, we could also explore other boosted decision tree models because there is XGBoost, but there are other kinds of boosted tree models out there. And then one more thing that I have here depicted, there was a trade-off between precision and sensitivity throughout us training and testing our models that is also consistent with the literature. So I did find that interesting. This is a depiction of the curve between precision and recall for our high-performing XGBoost model. Consistently, we did find that with the more students that were correctly identified as dropouts, less dropouts themselves would be accurately identified as dropouts. So we had to figure kind of balance between those two, and that was kind of what drew us to use the F1 score as the main metric to use for our research issue. But that was also something that we encountered which was consistent with literature. So in summary, for this project, we looked at various models, statistical supervised, and incorporated a number of data processing techniques as needed. XGBoost, mice, and SMOTE make up the most optimal technology methods combination for forecasting dropout. And here I have the references that I'd use throughout this slide show. Okay, thank you for listening in.